Well, hey there, it's me, Miss Wesley, for some calc time again, as you're joining me on the continuing saga of finding volume of solids of revolution. And today we embark upon using the washer method. Earlier we were using circular discs, circular filled in discs, to integrate area of a circle to get volume. And today we're going to see washers. We're going to see discs with hollow insides, like these washers. I can see right through this. Makes me think of the shape of a donut. I'm on page 11 here in your volume packet, and I see this nice, delicious looking donut at the top. I didn't have donuts to bring with me, but I do have all these bagels. And bagels are like donuts. They have a hollow inside, they have a hole through them. And it reminds me of a joke about donuts. Knock, knock, who's there? CIA. CIA who? CIA ate your last donut. Uh-oh. All right, so I'm looking at the warm up at the top and I see a circle with a hollow inside. So you have this big 11-inch radius on the outside, and then you have a hollow inside where the circle just has a 7-inch radius. And I feel like area-wise for this 2D figure, we could use the big radius minus the small radius in one area calculation minus another. So maybe this would be something like big area, so a pi r squared with the 11 inches, and then minus a pi r squared with just the 7 inches, right? To get like a 121 pi minus 49 pi. And that should just leave me with 72 pi square inches of area. And the key part to this was just doing outer radius minus inside radius. So we get rid of that hollow inside. And today we're going to see shapes like we see on number 1 here on page 11, where you're spinning a region around an axis of revolution, and the region isn't pressed up flush against that line of revolution. So what I mean is you've got just the region here bounded between y equals 2x and y equals x squared, but you've got all this empty space between the shaded region and the line of revolution, the y-axis for this one. And that's going to create a disc like you see here with a hollow inside, more of a donut shape because it's got an inner and an outer radius. Let me try to draw one more washer here. So you've got all the way to the outside, all the way to the outer line, which is going to be the y equals x squared, the curve on the outside. And then you just have the inside that only goes to the line y equals 2x. We've got two radii at play, an inner and then maybe a longer one. What can I use? Green for that, to the outer radius there. Sometimes my pictures aren't the best. I set this one up on a computer program, and I just want to revolve this region that we're shading from the get-go around the line x equals 0, or the y-axis. So it revolves around, and you're going to see the outside of this shape. We can see through this. The outside of the shape is going to be filled in, and then the inside is really going to be hollow because we're talking about using a washer here instead of a disc. So on our picture, what can we do? We've got, like we said, two radii involved in this, and they're both variables. Now I notice in this one, we have a line of revolution that is vertical, right? So we want to do this whole problem in terms of y's instead of x's. So that means I want both equations in terms of y's too. So I'm going to say my inner radius is just the distance, just this horizontal distance from the y-axis up to the line y equals 2x. And my outer radius is this green line all the way to the outside to the curve. So let me get both of these equations in terms of x equaling something with y. So if it's y equals 2x for that line, and I solve that for x, I've got to divide both sides of the equation by 2. So x would equal y over 2. That would be the line. And then if, same thing here, if y equals x squared is kind of like the outer curve to this, we could solve this for x, make it the square root of y. Technically the positive or negative, but let's just talk about the positive for now. So like I was mentioning, we have an outer radius, and let's just nickname that capital R. Outer radius is going to be big R. And let's think of that. Outer radius is the horizontal distance from the y-axis all the way to the outside of the curve. So it's this distance here, all the way out to the square root of y, right? X equals the square root of y. Versus inner radius, we can nickname that lowercase r, little r. And that will just be the distance from the y-axis to the line, this inside radius of that hollow part of that washer. So we're going to say, what was this? X equals y over 2. is going to represent your inner radius, just to the line. And when we integrate, we do this thing called the washer method. And we want to take outer radius calculation minus the inner radius. We're going to use volume. And for this one, we're integrating, like we said, with everything with respect to y. So we're going from one y value to another. I wonder how much we can see in the picture. This looks like it goes from y equals 0 all the way up to y equals 4. So I'm going to use those for my limits of integration, 0 to 4. And it's pi, right, because we have a pi r squared. We're going to do a big pi r squared minus a little pi r squared. An outer radius calculation minus an inner radius calculation. This is in terms of y, so I'll just preemptively put a dy there. Now there's pi in both parts of this, in both area calculations. So for this, if we want to pull a pi out, like GCF it to the outside, we'll probably be better off. And I'll pull the pi to the outside of the integral sign, and we need to figure out it's still 0 to 4, big radius squared minus little radius squared, all with respect to y. And that's why we set ourselves up earlier, right? We said outer radius was going to be square root of y, whoops, and then inner radius is going to be y over 2. So let me use that. So outer radius we just said is square root of y, and that's all squared. And then separately, inner radius squared is going to be this fraction, y over 2, and that is squared. So we did the toughest part of the question. For this washer method, we're going outer minus inner. We do want to simplify through the parentheses before we take an integral, so we'll do that next. We'll say volume equals, here's the constant pi on the outside. We want integral from 0 to 4, and what is this? The square root of y, but then squared, so that's just y. And then minus, let me square the top and square the bottom. So we'll make this y squared over 4. And this one, let's see through the whole way. So let's take an integral, leave the pi. So we'll go y squared over 2. And then what would the next part be? We're going to take this up to y to the third. And there's going to be a 3 to join the 4 that's already on the bottom. So divided by 12. Evaluated from 0 to 4. I'll leave this next part to you. Plug in 4. Technically, you subtract what you get when you plug in y equals 0. And then just so you can check your answer, right, let's plug a 4 in. So pi 4 squared over 2. And then minus 4 to the third over 12. And then minus 0 for the next part of it. So we can make this lowest terms fraction 8/3 times pi. 8 pi over 3 cubic units. So at the bottom of the page here, it kind of just gives you a rule for any time we might need to apply the washer method to be able to find volume of a solid of revolution. Here's how you know it's a washer question. If your shaded region isn't pressed up flush against the line of revolution, like you've got this empty space in between this and the line, you're going to get the original shaded region, but you'll get this hollow inside. Like this whole thing should look like a wheel or a donut, should be more 3D with this hollow. I could see right through it, like I can see through this washer, right? Same thing here. If this little crescent moon shape region is spun around this axis, you'll get the insides filled in, but then you'll get the outside, you know, like actually if you look at the inside, it'll be hollow. This should look like what we just used for that calculation. It's just that the pi is pulled to the outside already. So pi is GCF'd out. It's one big pi r squared minus one small pi r squared, always for the washer method. So I want to skip down. Can we look at on the next page, maybe just the 2 practice questions starting with number 3? It says, okay, the region enclosed by the curves y equals x and y equals x squared is going to be revolved around the x-axis. So at least these are things where we're familiar with their graphs, right? We've got y equals x, so that looks like just this straight line going this way. You've got y equals x squared, and the region enclosed is revolved around the x-axis. I'm going to only use the positive side of this as well. I'm just going to use the in quadrant 1 version of this shaded region. So just that part of it, right, enclosing those curves. I want to spin it around the x-axis. So imagine this little shaded region, it isn't pressed up flush against the line of revolution. There's some empty space. So this looks like a washer question as well. In 3D, this shape should be spun around the x-axis, should give you a hollow inside. So big radius squared and then small radius squared for the inside, making this a washer question, not a disk. And this one has what? A horizontal line of revolution. So we can think of this using x's throughout this entire problem because you're revolving around the x-axis. So we still want to do volume. We still want the pi pulled to the outside, but we have to integrate a big outer r squared minus a small inner r squared. And then we'll do this all with respect to x. We pull our normal tricks, right? We use normal methods to get the intersection points. And this, it wouldn't take long to see these two are going to cross each other's paths from 0 to 1, right? They intersect at 0, 0, and these two graphs intersect at 1, 1 as well. So I'm going to use these two x values for the definite integral, and then we got to come up with expressions for our outer and our inner radius. So for this one, I got to look. Inner radius, let me highlight this in green. Inner radius should just be the distance up to the curve, while outer radius should be all the way up to the line. So I want to do big R for outer and small r for inner. Outer, take yourself all the way up to y equals x. So in terms of x, we'll say big R, outer radius, should just be this distance x all the way up to the line. Inner should fall short of that. Inner should just go up to the curve, so it should just go up to y equals x squared. And that can organize, right, what we're putting into this integral. So if this is outer and this is inner, we'll take these back to the integral for volume. So pi comes to the outside, 0 to 1 for the x values. Big R squared should just be x squared minus little r squared should be x squared squared. We're going to integrate with respect to x. So neither of these terms should give us too much trouble either. This is going to be pi, integral from 0 to 1. This is just x squared minus x to the 4th. And we'll take an integral, so these go up a power, x to the 3rd over 3 minus x to the 5th over 5, and evaluate from 0 to 1, right? So the 1 goes in first. We'll say pi 1/3 minus 1/5. And we end up exact fraction with 2/15, 2 pi over 15 cubic units of volume. Okay, let's look at least setup of one more. It says find the volume of the solid obtained. Now we've got a different line here. Rotating the region. Oh, so it's the same two curves. So y equals x and y equals x squared, but we're spinning it around a different horizontal line, the line y equals 2. Now, since this is horizontal, we know we're good to go with using x's in this problem, but we're going to take that same shaded region. Here's y equals x squared, and here was y equals x. And this time, we're going to spin it, because it kind of goes just from like 0, 0 to 1, 1, but we're going to take the line y equals 2, and we're going to spin this shaded region around this horizontal line. I notice again I have a lot of empty space. This crescent moon shape isn't pressed up flush against the line of revolution. So you'll have something like this, right? These two filled in outsides, and then you've got this hollow inside of this shape. Maybe I switch colors while this gets a little bit sloppier to green, where you have outer radius squared, and then you have small inner radius squareds for the hollow inside of this shape to use a washer. So for this one, I want to do outer big R, and I also want to do inner small r, inner, a little bit sloppy. So big R, right? Let's think of top minus bottom function. For big R, let me switch to purple, and the top function is y equals 2, and the outer bottom function is all the way down at y equals x squared. That takes you to the bottom of the whole shape. So we're going top minus bottom minus x squared. Top, we'll say t for top minus b for bottom. For inner radius, you just don't go quite that far. For inner radius, your top is still y equals 2, but the bottom, you're going to stop short and only come down to the line y equals x. So this would be 2 minus x for top minus bottom. And this at least gets us to the setup of our integral. We're going to integrate volume. Let's bring the pi to the outside. You're still going between two x values, so we're still between the old trusted 0 and 1, but you're doing outer radius squared, so 2 minus x squared, and then minus inner radius squared. That would just be 2 minus x squared. So lots of simplifying to do here. You've got to FOIL this and FOIL that to combine the like terms. You got to take an integral. You got to do the plug-in after that. But this was a big feat for us, just kind of getting our feet wet with the washer method and seeing you've got that empty space, and sometimes you can use a top minus bottom as well. Okay, hope you have a wonderful day and excited to talk to you about this stuff soon. Have a good day.